Hey, right, so this topic is a little bit more complicated than the other ones we've done, so I can't just send you a PowerPoint because I think I'm just going to totally confuse you all. So I thought I'll try and send you a video, see if this works any better. So we're going to be doing about electric fields. Now, they act basically like batteries. So if you've got two that are the same, they're going to repel. Okay, so if you've got a positive and a positive, they're going to repel. And if you've got a negative and a negative, they're going to repel. So obviously, if you have a positive and a negative, they're going to attract. Right? Now, this gets a little bit more complicated because you guys actually need to know about what the field around these things look like. So this kind of counterintuitive because in the past we've always told you that the negative particles move, the electrons can hop around, but the protons have to stay stuck in the atom. But that's not actually how we draw it. But don't ask me why, we're basically lazy and we haven't changed it in science, but that's another matter. So in a positive particle, the field lines move out as if like the positive particle's doing the moving. And then the negative particle, we draw the lines coming in. So it's a kind of like a north and a south pole. So out of north into south. Okay, now we always draw this for the particles. So I'm just going to give you a few seconds, but obviously like pause the video. Draw what you think they look like between two positives and draw what you think they look like between a positive and a negative. But I'll give you some time. Right, so hopefully what you've kind of got drawn is something like this. So it, as I said, they always come out of the positive. So they should do this. Whoop. Because this doesn't want to go near that. So, whoop. And then these ones just come straight out. And then whoop. So it should look like that. Okay. This one's way easier. So it goes always out of positive into negative, which means these guys are going to be trying to attract. Let's go do that. And if you want to be like extra vigilant, just in case the examiner is like, oh, I wonder what they mean, just draw these as well, just so they know that it's definitely going in. Equation of the day. Right. So this is going to get complicated very, very quickly. Now, I can't explain the derivations of the equations. I'm not going to, because you don't need to know it. It might make some of you understand it a teeny bit better, but as long as you can use the equation, it does not matter, okay? So force is measured in newtons. You should know that from GCSE. Charge, symbol Q, measured in coulombs. Now, this is new. It's a curly E. It's not like a capital E. It's a Greek letter. So it's E0, and it's something called the permittivity of free space. All that means is how easy it is for like fields to move through something. So in a vacuum, it's not got a material there. That's free space. So everything's kind of gauged against that. So this is kind of like a constant for us that we use. So we always use this number. And then R is your radius between the two charges. So, if you've got charge here and charge here, it's the distance between the two. And as you should know, that's measured in meters. So this, as I said, it gets complicated very, very quickly. This is our equation. So the force between the two particles, so like a positive on a negative, how much it's pushing it or pulling it towards it, is the charge of one of the particles times by the charge of the other divided by 4 times pi times this permittivity times by the radius squared, okay? Now it's sometimes written as this, and K is just 1 divided by 4 pi epsilon naught, which is permittivity, okay? So just imagine we're taking that out and we're just putting 1 over it times the Q1, Q2 over R squared. It's the same thing, but just be careful because I'm not sure how it's written on your data sheet. I think it's this one. So you need to be aware that that means this. Now, I've made it a teeny bit easier for you, and every other class in the past has used this instead. That is this number, 8.99 times 10 to the 9. If you just remember, you do 8.99 times 10 to the 9 times by your charges divided by your radius squared. It's much easier than trying to fumble through your data sheet and finding these numbers. Just remember that. If you can't, don't worry, because you know that this means 1 divided by the 4 pi epsilon, your permittivity. But if you can't remember it, it's there, but it's easier just to try and remember that number, okay? So I'll put that there for a sec just so you can write it down. Okay, right, let's see how much you've learned. So this is a question. I want you to have a go at answering it using that equation I just showed you. So pause the video here and have a go, and then I'm going to walk through how you do it. Okay, so find the electrostatic, I'll try and colour code it to make it easier. Find the electrostatic force between a 3 microcoulomb charge and an 8 microcoulomb charge. They are 25 centimetres apart. So again, you're going to need to know what your conversions are. So micro is times 10 to the minus 6. So Q1 is 3 times 10 to the minus 6. Q2 is 8 times 10 to the minus 6. And remember, you can't leave it in centimetres, it's got to be in metres. So your radius is 0.25 metres, right? So now we need to plug these into that equation. So your equation is, F equals, 8.99 times 10 to the 9 times Q1, Q2 over R squared. So it's 8.99 times 10 to the 9 times 3 times 10 to the, if it's easier, put this bit in brackets, 10 to the minus 6 times 8 times 10 to the minus 6 divided by your 0.25 squared, okay? Now, if you plug all that into your calculator, what you should hopefully get is, let me just double check mine, 3.45 newtons. So that's your force, okay? So have another go if you didn't get it right and follow through what I did. Hopefully that's the number you should get, okay? And then we'll need to move on to the next step. It's electric field strength. Now, this is a much easier equation. Your electric field strength is your force divided by your charge, but it's the test charge. So if I've got a charge that's there and then we've got one that's being sent through to test it, we're only talking about the dude that's being sent through. So he's the only one you actually consider moving, okay? So, just so you know where the unit comes from, force is measured in newtons, charge is measured in coulombs, so your electric field strength is newtons per coulomb, so newtons per coulomb, or n to c to minus 1, okay? So don't forget your units in your exam. Remember, you can pick up very easy marks for using them. Now, there's a question down here. Because this is such a simple equation, I mean, you've only got 2 things to think about here, and the fact it's a test charge. What I want you to do is have a go at answering it, and then obviously I'll walk through it again, but I'm not going to give you as long to do that, so just, you know, this shouldn't take you more than about a minute to do, really. Work out what the test charge is and plug it into that equation. Okay, so a 3 microcoulomb charge is used to test the field, so that must be the test charge. So that's your test charge, okay? This is the thing it's going through. We don't need to worry about him. He's not the test charge. And what is the magnitude of the electric field if its force is 800? So that's your F. There's your Q. So all you literally have to do is E equals F over Q. F is 800. And then, again, don't forget to convert. That's micro. It does tend to be in micro. Most your charges are micro. So if you just remember it's round about times 10 to the minus 6, it makes things easier. So that's 3 times 10 to the minus 6. So that comes out to be 2.7 times 10 to the 8 newtons per coulomb. Easy. Now, the other bit you need to know is about what the electric field strength looks like in terms of graphs. Now, this has never, ever, ever come up in a paper, but it's in your specification, which means Sod's Law will be, it will come up on your year. So I just want to make sure we cover it. But again, I've never seen this come up. It's just a relationship. So it's what happens to your field strength as you get further away. Well, you know, it does this. So using your knowledge from GCSE and what we've already done, have a go at describing the relationship between the two. So what you should have said is, as the radius goes up, the electric field goes down. So as radius increases, the electric field decreases. So this is an inversely proportional. Inversely proportionality, which means as one goes up, the other one goes down. So as radius goes up, the electric field goes down. Easy peasy. Here's the last bit of equations I'm going to do today, because now I'm kind of like overloading you. This is the electric flux density. Oh boy. Right, so D is the flux density, and it's measured in coulombs meters squared, or sorry, coulombs per meter squared. Now this is your flux density. It looks like a trident almost. Now this is just basically your charge. It's even measured in coulombs. It's, you know, when you have lines like this, that's a flux line, that's a flux line, that's a flux line. The amount of flux lines in a given space is the flux density, which is what we're trying to calculate, okay? So that's a symbol for one of these lines, basically. So flux. And A is the area in which you're looking at, yeah? So you've got D is your flux density, that is your flux, and A is area. You should know that area is measured in meters squared, okay? This is the equation we use. So the flux density, so D for density, easy peasy. D is your flux divided by your area. Now, this is really common sense. Which is stronger? It's the one with the most lines, yeah? It's like contour lines when you do geography. So these have got more flux lines in a given space. So if I was to do that, I've got 3 flux lines there. Well, if I was to do that here, I've only got 2. So this is going to be a stronger field. So more stuff's going to happen quicker in here, okay? That's all you're calculating with this. It's really easy, very simple equation. So make sure you've got it written down. So the last question of the day from me. A 3 microcoulomb charge is travelling through a material which is 3 centimetres wide by 6 centimetres high. What is the flux density? So pause the video and have a crack at it, and I'll walk through it in a sec. Okay, so always work out your area first, which is going to be 3 centimetres by 6 centimetres. Convert them to metres before you get yourselves muddled. So 3 centimetres is 0.03 metres. 6 centimetres is 0.06 metres, which means your area is 0.03 times 0.06, which gives you 0.018 metres squared. So do that first. Always do that. 0.0018 metres squared. Okay. So now you need to find out your actual flux density. So you know your equation is your D equals your flux over your area. Our flux is 3 times 10 to the minus 6. And your area you've just worked out to be is 0.0018, which means your answer comes out to be 0.0017 coulombs per meters squared. Okay, so there are all the equations I'm going to give you today. Yes, there are more to come. I did tell you this is a difficult topic. You know, this is second year physics, A-level, and I did this in the first year of my degree. So please take the time to watch this over and over again and get it right in your head before we move on to the other things, okay? I'm going to send some questions out tomorrow for you to do, based on all of this stuff. So make sure you watch this video first, again and again, and then have a go at doing those questions. Good luck!